Welcome to another GCBASIC tutorial for the 16F175 chip family. This is part 13. Let's wait for the logo to complete and then I'll move to the second page. So this is part 13 using SPI, Serial Peripheral Interface, and I'm going to be using a GLCD to demonstrate that. It is purely a device I've chosen. It could be a memory device, but that's not so simple to see working. So this is for the SPI Serial Peripheral Interface GLCD. Please like and subscribe the videos. I'm in this for the like and subscribes, and it's important that those metrics come through. Great. So this is part 13. We're going to go into another complete different area very soon, but SPI is a different module within the microcontroller. It's a different library, different setup. So it's important that you understand the simplicity of its use. So I'm assuming that you've got everything installed, your programmer works, you have a 16F175 attached. You don't need the LEDs, pots or switch this time, or the TTL, but you do need the SPI device, and I'll show you what model that is very shortly. So what is SPI? Serial Peripheral Interface. It's an interface bus. It's used between microcontrollers and a GLCD, registers, shift registers, sensors, serial cards. The SD cards are serial SPI devices. And it uses a clock line, a data line, and a select line, which means that you can have multiple devices that you can control. So you can actually talk to a device or multiple devices, but not at the same time, by using the control line or select line. Now, a point of interest here is that I'm going to be using certain terms. These terms have changed in the last 10 years. So some documentation will refer to other things in SPI. If you look at the bottom left side of this slide, it does say what those have been changed. So I will be using the more modern naming, not the older one. So what we're doing is connecting this SPI device, and there's a circuit that I put in, and I'm using port C. So I pulled out everything that was in the previous tutorials and I put this in. So port C, I don't have that TX1, so that should not be there really, but I've definitely got an SDO, serial data out, serial clock in or clock. And then I've got this chip select or CS line, but I've also, this requires two more. It requires a reset line, and that's something on the hardware itself. And whether you are sending a data packet or a command packet, and it's called the DC line. So you've clearly got 5 connections to this GLCD. You might only have 3. You might have a reset line or data control line when you use a memory device. But typically you're going to have 5. So what does that look like? Well, it looks like this, because we're not going to get the opportunity to zoom in on that GLCD. We're going to see it operating, but it's pretty tough to see it. So why don't actually what I'll do, control, I'm going to print that screen out a bit bigger, look. I'm going to bring that up and bring it in much larger so that we can see it. There we go, much larger. And I'll just go back into my slide. I'll make it even bigger, look, so we can see it, look. Back into my slide so we can see it. That's here. Now, what we've got is a set of connections. We've got, I'll use my pen. We've got ground. That's 0 volts for me. VDD, I'm operating mine at 3.3 volts. It's only tolerant to 3.3, so I'm operating my whole board at 3.3. Check your voltages. Yellow for my clock line. Serial data. Now this says SDA. Isn't that clever? I'm using SDO. It means the same thing. That's where people get confused. Serial data out. The reset line is res, DC for data or control, and this is the control line. control select. Now, if you don't have more than one device, you can strap the CS to high or low, depending on what the board requires. But it means there you have 4 lines, but you can only talk to one device. So the chip select or CS line, I'm going to show you controlled from within GCBASIC, but you could strap that to either high or low, depending on what device it is. Now what I'm going to try and do is go back to my slides, and I'm going to guess the page number that we were at before wow, that wasn't bad actually. That's what we were looking at. So we've got a load of control lines, and I've used yellow and blue for the clock and data line, and I've got other colors involved. So why don't we have a little look on that on the desk cam, okay? So here it is. It's actually running at the moment. Here's my chip here. It's upside down in terms of labels. And I've got my flying leads coming out from my bank of connectors here and into exactly where I've just been showing you in the picture. Ground VCC, clock data reset, DC and CS. And you can see it working. So it's a small board, but you can get bigger ones. It's up to you. Go get bigger ones, get smaller ones, etc. But we'll see that working in a minute. So how do I set up? I look in the documentation for the help, and I look up this particular device. Well, I've got a particular device, and it's called an SSD. That's its model number, SSD 1331. That's what it is. And we'll look that up inside the data sheet and inside the help, or I look at the demonstrations, and it will tell you that you need 2 defines, one for the data out and one for the clock, SCL. And then you need 3 control lines, the DC, the CS, and the reset. So I must have 5 connections on my board. One other thing you'll see in the help is this. It says use SSD Hardware SPI. SSD 1331 _ Hardware SPI. You can use software or hardware with the libraries, and we'll use both. And that's sort of important to make sure you get reliability you make sure that you've got your connections working before you dive into the hardware. So typically I would start with that commented out. We'll look at that in the program. Because you can hook it up, and here's a hookup on a board, and it doesn't work. Let's pretend it doesn't work for a minute. Well, there's some things we do know. We do know that I'm demonstrating this particular chip with that board and with that display working. Therefore, we know the demonstration works. It's not likely to be the library that you're going to be calling, because it's likely to be something else. So the checklist. 1, check your connections. Not once, but twice. Don't put a support ticket in on SourceForge until you've checked your connections twice. Write your own program to pulse each line. Start with the clock, then the data, each line, and check it works. Just pulse the line out and then put a meter on it or LED and just check the line is actually working on the microcontroller. And then check it on the actual SPI device. That will just check you've got continuity backwards and forwards. And that continuity might be, you could put a meter on it, you could make it high or low, but check the line. Always use Software SPI to prove your connectivity. Once you know you've got the software version of the GLCD driver working, then in this particular model, you can use the PPS to set up the hardware. Only if number 3 works, because it's not going to work. If the software didn't work, the hardware is not going to work. They are intrinsically linked. So linked in terms of the data line and clock line will be controlled in the hardware by PPS, but the other 3 lines are software, so they need to work. Checklist, use it. So what we're going to do is going to have a look at an operation of a GLCD. We're going to look at Software SPI and then look at Hardware SPI using, of course, PPS. And I'm going to show you something called conditional compilation. What happens when you do different things. Okay, Let's have a little look, go back to where we were before. Actually, I won't. I'm going to go into GC Studio, start up GC Studio, and select, as we've seen that before, we're going to select these particular chip range demonstrations. Click, I've selected that. I'm now in the IDE, but you can't see it. It's on a different screen here. There we go. It's just appeared on your screen. Great. So let's open up the Explorer, Shift Control E, Control B, or top left-hand icon. And we're going to open up demonstration 230 SPI GLCD using an SSD 1331. That is the type of device I'm using. Could be. And you can adapt this to use RAM or whatever. But I said that using a GLCD device just shows you graphically that things are happening. I've clicked it. I've clicked inside. Control B to shut down the Explorer. Let's walk from the top. Define the chip. Oh, I should zoom in for you. Define the chip, option explicit. Anything in green's comment. So let's not worry about that. Now, I'm going to show you the setup of the GLCD. Okay. I've said here, I want to include the GLCD library, and I want a GLCD type of a SSD 1331. That is different from what we saw in the previous tutorial. So it is important. And I'm going to test this with software. So I just need to comment out / you can use comment, you can type rem, semicolons, whatever, or you can press control / and it will then just comment that line out. And once I've done that, it's going to turn on the software SPI. And then I need to define my 5 connections. Data out is on C5, the clock SCK is on C.4, the data control line is on C.0, the chip select is on C.1, and the reset is on C.2. Now all these are in these demonstrations, but they're also in the help. And that's all you need to set it up. That looks too simple, doesn't it? Yeah. You need to go include the GLCD library, define what type it is, and then set the ports up. But if it's software, I want to teach you something. Unless you turn off the chip completely and reset the whole chip, you might end up with the PPS that was from your previous run still working. So let's look at what's going to happen at the top. We are using software. So therefore, we do not want to use PPS, peripheral support. Well, here it is. Look, I've said if def, else, end if. But this is strange. It's got a hash in front of it. Well, that hash means conditional. It will change the program depending on whether this is a constant that is defined. I've gone to PPS tool, which I will show you briefly, and I've taken out the piece of code that I need. And I need let me zoom in a bit more. I need this bit of code here because that is my PPS setup. RC4 and RC5 are set up to support this particular SPI protocol. Let me zoom back out. But they're inside of this conditional. They're inside of this conditional statement. So they'll only get used if hardware SPI is a constant that is defined. Else, the normal case, in our case, I'm going to set the PPS to 0, this clock thing to 0, and this port PPS to 0. What they are is going to set them to 0, which means revert the capability of that port back to normal, because that's what we need. We don't want the PPS controlling it. We want to use our own software registers, and the library that we're using will just bit bang. It's called bit banging. It will send the data out and magic will happen. It gives the bit banging simulates the clock line and data line. So in our program, I have got a load of code. Do you know what? I'm not even going to show you much of it. It's going to put some strings on the screen for us. It's going to change the color by using the clear screen. It's going to print some stuff. It's going to change the color. And then it's going to go into a bit of a routine to show you how to draw boxes, circles, lines. These are exactly the same commands as we saw on the previous demonstration and tutorial. Function key F5. I'm now programming it. I'm just going to leave that running. Whilst that's doing that, let's have a look what we expect to happen. What we expect to happen is the initialization will set all this to 0, ports. Oh wow, that's wrong, look. That's C.5 that should be, look. I'll just change that. C.5 will be set to 0. This PPS, a bidirectional port that's set up, will be set to 0. The clock line on C4 will be set to 0. So it will be in software mode. We'll just ensure that we're in software mode because in here I've got this commented out and then I've got my 5 ports defined as I showed you in the tutorial presentation. The rest of this is graphics code. Let's have a look what's happening over here. It's black. Have I got any power in the board? Now, I showed you that that line was wrong. I showed you that I was setting A.4 to 0. So I'm going to power cycle the chip. And voila, it burst into life. It only burst into life because the PPS ports are now free. They're set to 0. You can see it's doing stuff, okay? I'm going to zoom in. Let's try and get a bit closer. Can I get any closer? Nope. Let's zoom in this way then. Hey, look at that. That's worked. I'm moving the camera. It's easier. I can't stop the flicker. That's because I've got conventional lights in the room here. Now, if I press the reset button, have we got a reset? No, if I power cycle it's a good way of doing it. Look, there you go. Put some text on the screen. Therefore, the SPI is working. We know the data lines are right. It said blue, it's gone blue. It did say red, by the way, and I can't see that flicker, by the way. I cannot see it on this display here. Long numbers, big numbers, circles, squares, etc., etc. We've got SPI working. In your mind's eye, it's updating that about every second. So in my program, I'm going to come into here and I'm going to get rid of that comment and I'm going to define the hardware. And this time when it does it, we program it, it's going to conditionally turn on the PPS. Now it's writing out. So what it's going to do this time, because this constant is now defined, it will set RC5 and RC4 to these PPS values, and the clock for bidirectional purposes will be set to hexadecimal 14. Now those are important. There's nothing. Those specifications in the data sheet, and PPS tool gave me those values. Well, one of the beauties of this is I can change between software and hardware SPI because the graphical library that is defined supports both. I want to turn on the speed on my programmer really. Now, in here, nothing else changes. All this code is identical to as it was before, but it will be about twice as fast. We'll just see that come. And you can see it is faster. But this proves to you that the SPI library is working. Therefore, the clock line is working, the data line is working, the reset, chip select, and the data control line are all working because it's working in both software mode and in hardware mode. Any good library would support both. You just need a constant to change. Okay, that will do. Next, pulse width modulation. Many ways to dim those LEDs. We're going to show you at least 6 ways of doing pulse width modulation from simple to complex. Meanwhile, enjoy this tutorial.